Hello everyone. I wanted to give you the homework solutions like I usually do, but I figured that since I am now have this video recording set up, I might as well record myself going through the solutions rather than just type them up and send them to you in a PDF. So let's just go through the homework problems. I suggest you pull up the homework in a PDF next to the YouTube video. Because I won't rewrite the problems, but I will discuss them out loud. So what's problem one? Problem one asks us to write out the addition and multiplication tables for Z8. And this is just a matter of writing them out. I'm just going to do the multiplication table. The addition table is also simple. So we write out all the representatives for elements of Z8, so all the congruence classes modulo 8. So they're represented by the numbers from 0 up through 7, 6, 7. And then we just fill it in. So we multiply the numbers together and then take their congruence class mod 8. So 0 times anything is 0. So this entire first row and first column is 0. One times anything is that number back. So the second row and second column is just those numbers repeated back to you. This is going to be always true for every Zn. But the first row and first column are always 0, and the second row and second column are always just those numbers repeated back. And now we actually get into the multiplication. So 2 times 2 is 4. 4 is not less than 8. It is less than 8, so I just put a 4. 2 times 3 is 6. 2 times 4 is 8. 8 is just a 0 mod 8, right? I use the division algorithm, and I take the remainder. There's no remainder when I divide by 8. 2 times 5 is 10. 10 divided by 8 is, the remainder is 2, so I put a 2 here. And then I keep going. 6 times 2 is 12, which is 4 is the remainder. 6. 6. 9 is 1. 3 times 4 is 12. It's 4. 3 times 5 is 15. 15 is 7. 6 times 3 is 18. 18 is 2, because it's 18 minus 2 times 8. 5. 0. 4. 16 is 0. 20 is 4. 24 is 0. 28 is 4. 10 is 2. 5 times 3 is 7. 7 is... it's 15, 7, 4, 21, or 25, so 4, 25 is 1, 6 times 5 is 30, 30 is 6, mod 8, 35 is 3, it's the 3 more than 32. Now we're almost done. In fact, we can fill in this bottom row here because multiplication is commutative, right? So 7, 6, 5, 4, 3. 7, 6, 5, 4, 3. And I'm guessing this is going to be a 2. 6 times 5 6 times 7 is 42. 42 is, 4, 3. Yeah, it is 2 more than 40. 7 times 7, 49. It's 1 more than 48. And now to fill in this row, 6, 4, 2, 0, 6, right? Multiplication is commutative, so this column should be the same as this row. And then this is 36, which is 4 more than 32. So here's the multiplication table. And the addition table is done in the same way, but instead of multiplying, you add, and the pattern is much simpler, so I'm not going to write it out. Okay, so now we want to identify which elements are invertible and which are zero divisors. So I can look at this row, and I can check it in 2 ways. So first I can use the GCD condition, right? We know that an element is invertible if and only if its GCD with the modulus, in this case 8, is equal to 1. So we're looking at all the numbers that are coprime with 8. And since 8 is a power of 2, the numbers that are coprime with 8 are all the odd numbers. So this one is invertible, this one's invertible, this one's invertible, and this one's invertible. And I just need to find what number when I multiply it by 7 gives me 1. So 7 times 7 is 1, 5 times 5 is 1, 3 times 3 is 1, 1 times 1 is 1. So this is something that doesn't always happen, but does happen modulo 8. That the inverse of every invertible number is just that number back. Now, the zero divisors are exactly the even numbers. And you could call 0 a zero divisor. It's a matter of convention here. I would call it a zero divisor because you can multiply by something non-zero and get 0 back. So you can see that 0 appears for 2, it appears for 4, and it appears for 8, and 1 doesn't appear. So the zero divisors are not invertible, and the invertible elements are not zero divisors. So either 1 appears, and if it appears it's unique, or 0 appears, and 0 can appear more than once. So this is problem 1. Let's move on to problem 2. So problem 2 is a proof-based problem. So we said we defined addition of sets. This is just a recalling of definition. We said that the sum of 2 sets A plus B is an arbitrary sum of an element of A plus an element of B. So little a belongs to big A, and little b belongs to big B. So here's our definition of set addition. So now, M and N are assumed to be coprime. It's a good idea to write down what the assumptions are. So this is my assumption. And I want to show that for any A and B, the congruence class modulo M for A plus the congruence class modulo B for N is all of the integers. So this is what I want to show. And so let's write a proof. So this is something you might write, scratch on your own, just to have your list of assumptions. And now here is where we would actually write down the proof. And you may not come up with this immediately. You may write some more notes before you write it down. But proofs should be written down carefully. And it should be very clear what the assumptions are and what the conclusions are. So at the start of every proof, you should write down what the assumptions are. So we need to know that M and N are coprime. So the first thing we'll do is say let M and n be coprime, and a and b be integers. Okay, so once I write the sentence, these variables are fixed for the rest of the proof. I can't change them. They're determined. Now I need to show two things, right? What's the goal? I want to show a set equality. So whenever I want to show a set equality, remember that I need to show one inclusion and another inclusion. So one inclusion is very clear, that this set is a subset of the integers. Because this set is a subset of the integers, this set is a subset of the integers, and whenever I add two integers together, I get an integer. So notice that a sub m plus b sub n is a subset of z, since taking sums and products of integers gives integers. The only thing that could cause us problems is if we divide, right? Sometimes if you divide one integer by another, you don't get an integer anymore, you just get a rational number, like 3 over 2 or 4 over 3. Okay, so now I need to prove the opposite inclusion. So we need to show that z is a subset of a sub m plus b sub n. Okay, so how do I show a set inclusion? I take an arbitrary element of the left-hand side and I prove that it belongs to the right-hand side. So I take an arbitrary element of the left-hand side, which is just some integer. And now what do I need? This set, the sum of two sets, is defined to be the sum of elements of the first set plus an element of the second set. So I need to show that C is equal to something in A plus something in B. So I'll call it A prime and B prime. So now what do I do here? I recall what it means for A prime to be in A sub m. So that is, A sub m is the congruence class modulo m. So I'm allowed to add an arbitrary multiple of m to A. So some k plus b plus ln for some k and l belonging to the integers. So notice that this equation, okay, before I actually do this, this is sort of the end of the unpacking, right? I now have a very simple equation just in the integers. What do I know? I'm looking for a solution of this equation. C, A, M, B, and N are all determined numbers. C was fixed here, M and N were fixed here, and A and B were fixed here. So I can't change any of those. The variables that I'm allowed to pick are K and L. For some K and L, these are the things I'm looking for to solve this equation. So I have an equation in lots of variables, but all of them are fixed except 2. So I need to be able to solve for these 2. And so it's natural to take all of my fixed variables to one side and just leave Km and ln on the other side. So let's do that. So notice that this equation is solved if and only if Km plus Ln is C minus A minus B. And when you see something like this, remember that this is an integral linear combination. Of M and N. This should scream that you can use the GCD in some way. And our assumption is that M and N are coprime. So this is where we can actually use this. Okay, so this is the equation we want to solve. C, A, and B are arbitrary integers, and M and N are fixed coprime integers. So let's remember what the GCD theorem tells us about coprime integers. So since M and N are coprime, the GCD of M and N is 1. This is just definition of coprime. So I can find specific numbers K naught and L naught, and I'm calling them K naught and L naught now because I can solve this equation when the right-hand side is equal to 1. And now I'm basically done, because what do I need to do to get this to be this? I just multiply both sides of this equation by C minus A minus B. K naught times M plus C minus A minus B L naught times N is just C minus A minus B. So we can solve the equation and the inclusion. If you go back through the proof, you see that the solution, the inclusion holds. Maybe I should say set K equal to C minus A minus B times K naught, and L equal to C minus A minus B times L naught. And that's the end of the proof. So I want to just comment a few things about this proof and some common errors that were made. So many of you were able to unpack and get to this equation. And what you tried to do was solve for K and solve for L. And when you do that, there are two things wrong with that. So let me just write wrong here. I mean, this will be true, but it doesn't quite work because it doesn't completely determine K. So if you start from this equation here and you try to solve for K, you'll get K is equal to C minus A minus B minus L times N over M. And then you'd similarly get L is C minus A minus B minus K times M over N. And you said, okay, I picked this K and this L, and that works. So the problem is that K isn't determined from this thing because L isn't determined, right? This is still a system, it's an overdetermined system of equations. So you could try to take L equal to 0, but then you need to know that m divides this number. And you could try to take k equals to 0, but then you need to know that n divides this number. So the difficulty, and that's what this whole argument structure is about, is being able to pick k and l so that I can get these things to be integers. So there's exactly two problems, right? You don't know that this is an integer, and it's not determined because I don't know what L is here, and I don't know what K is here. So and you can't sort of recursively go back and forth. It just won't work. Essentially because these two were both derived from the same equation. So trying to set up a system of equations with two equations derived from the same one is going to lead to an overdetermined system, and you're not going to get a unique solution. And that's another feature of this structure, is that these solutions are very rarely, if not never, unique. There are multiple choices of k and l, but we found one of them based on this choice of k naught and l naught. The last thing that I want to say is that this trick can work regardless of what the GCD is, but I can't get any integer. I'll only be able to get multiples of whatever the GCD is. So here's another exercise for you that you might think about to do to prepare for the exam. So let m and n be natural numbers, and the GCD of m and n be equal to d. So d is just shorthand for this GCD. Then the set of all integral linear combinations so where k and l are allowed to range over all of the integers, is just the set of things that are divisible by d. I need a new name for variable x such that d divides x. This is sometimes written as with the notation d times z. Right? It's you take z and you multiply it by d, so it's all the multiples of d. So this is a very good exercise. I encourage you strongly to think about it before the exam. I hope this helped, and I will see you later this week. Bye-bye.